click the red subscribe button right under the video and also the bell icon to get notification on any of our latest updates on our videos.
Good day everyone, welcome to Smart Bookai's tutorial video. Here we have a question on electronics that says that draw the circuit of a 10 bits current steering DAC with an LSB current of 1 microampere, feedback resistance of 20 kilo ohm, and determine the output voltage for an input voltage of the particular digital values given. So we're going to start by drawing the circuit of current steering DAC. Alright, so we can see the drawing of the 10 bits current steering DAC. It's 10 bits as because we have 10 currents here, which is we have ID note, ID1, ID2, ID3, ID4, ID5, then we have ID6, ID7, ID8, and lastly ID9. Starting from ID0, that's ID note, we are given from the question that it has an LSB current of 1 microamperes, meaning our ID note from the question is given as 1 microampere. Alright, from the circuit we can see that the positive terminal is connected to the ground. Likewise, we have switches on the DAC, and the switches have zeros and ones. So whenever we're having a 0 in the input, the switch will be switched to the 0, which is connected to the ground. As we can see, it's been connected here to the ground. So all zeros, which is this, and all the rest are all connected to the ground. While the ones, whenever we have the I1 as an input, it is connected to the negative terminal, which we call the inverting terminal. This is called the inverting terminal, which is the negative. So the negative been called the inverting, and the positive, the non-inverting. So we can see how the inverting provides a 1 and the non-inverting provides a 0. Now we can use this concept to solve this question. We are given our D naught to be 1. And from the principle of operation of a current steering DAC, the current at the LSB, which is at ID node, will be multiplying by 2 whenever it goes to a node. So we can see the current incoming here is we have 1 microamperes, and as it reaches this node, this particular current is going to multiply by 2. So, meaning at this point, which is our ID1, we have 2 microamperes. Now, coming to the next node, it's still going to multiply by 2 because that's the principle of operation of the DAC. So at each node, now every node, it must multiply by 2. That's the current. So since here we have 2 microamperes, just be multiplying everything by 2. So we have 4 here microamperes, and we have 8 microamperes. Then here we have 16, here we have 32, here we have 64, here we have 128, and so on until you reach to the last, which is 10. So, alright, since we're going to make use of 10 only, we can keep on multiplying by 2 until we reach the last one. So, what will be this place? 256, right? And then what about this one? We still multiply by 2. It will give us 512. So, we now have our complete currents that goes through each of the nodes. Mind you, each of the current like this is for ID1 because it passes through here. This is ID2, this is ID3, ID4, ID5, ID6, ID7, ID8, ID9. So we have our 10 bits DAC now. Now, after drawing the circuit, let's go to the real calculation. Okay, from the question, we are asked to determine the output voltage, right? Yeah. So, our output voltage in a current steering DAC is given by minus I R F. That's the formula for our current steering DAC. Now, we have our RF given. This is our feedback resistance, right? And it is given as 20 kilo ohms from the question here. So we have 20 kilo ohms for our RF. This I implies the total I we're having. So let's go ahead and calculate our total I. Our total I is the summation of all of the currents in the DAC. Now, we have, starting from the MSB, which is the most significant bit, that is our ID 9. We're going to sum all of them plus ID 8 plus ID 7 plus ID 6 plus ID 5 plus ID 4 plus, yeah, we're almost there, ID 3, ID 2, ID 1, and finally ID 0. So we have to add all of this, but we're given our input voltage to be 1011001101. So we have to keep that in account. Now, to keep that in account, anyone that says 0, we already know, like I explained before, it is connected to the ground. That means it is automatically 0. There is no current passing through it, so it's just 0. So we're going to take only those that are having 1s. So let's write it down for more clarity. We have 1, 0, 1, 1, 0, 0, 1, 1, 1, 0, 1 rather. Okay, now anyone that is having 0, we can cancel it out. So this one is having 0, we're not going to make use of it. 0. This one is having 0, that's our ID 4 is 0, so it's 0. ID 5, same thing, 0. ID 8, 2 can go because it's still 0. Now, let's go to calculate the ones that don't have a 0. Now, for the ones that are having 1, will now be equals to, we substitute for each of them. So our ID9 is having a 1. That means we're going to make use of our ID9. And our ID9 calculated above, we said it was 512, as we saw above. So 512 plus ID8 is 0. We cancelled it out. Then ID7, 128 plus our ID6. What's our ID6? We have it to be 64. Plus the next one, ID5 is 0. Likewise, ID4 is 0. Then ID3, what's our ID3? We calculate it to be, I think we calculated to be 8. Yes, 8. Then our ID2 and our ID1 is 0, so we're not using it. Then our ID0, which is our ID0, that's the initial one, is 1. So all you have to do is just add all this. Now grab your calculators. I'll also grab mine and we'll calculate the result. Well, after summing all these values, we'll get 7. Our values to be 717. Mind you, our unit is in microamperes. In engineering, units are very important, so we need to take notes of the units. Now we can go ahead and find our V0 since we have our I and also our feedback resistance. Now, our V output, that is our output voltage, V output will now be, have minus, and we got our I to be 717 micro, which is 10 raised to power minus 6, right? Times, what's our RF? Our RF was given to be 20 kilo ohms. So 20 and kilo, which is 10 raised to power 3. Now, still grab your calculator and you'll be having your answer to be 14, that is minus 14.34 volts. Like I said, unit matters. So with this, we have reached to the end of this question. I hope you liked the video. Thank you.